with me. So yeah, so today it's the part 2 of the common defects when welding stainless steels and how to avoid them. And it's a little different. Now, in the first session, Graham talked about some general details on stainless steel families, their composition, corrosion, a good section on why welds fail related to poor choice of material, poor design, incorrect or bad welding procedures, poor preparation technique, and insufficient post-weld cleaning. He also talked about some second generation ferritic stainless steels, the low chromium stainless steels, and then went through common defects, inspection, radiography, and how to avoid them, and then some good welding practices. So today I'm going to start off with a few case studies, and there's nothing spectacular about them. They are things that I have come across, and people have come to me and said, what went wrong here? Then we'll have one called Start Off Correctly, which is a very important one, which doesn't it goes beyond what is the welder doing. It actually starts off correctly so the welder can do his job. The biggest section will be on dissimilar metal welding. That is one thing that a lot of people have issues deciding what filler metal to use. We'll talk a little bit about repairs, and we'll talk a very little bit about post-weld treatment. So let's start off with the first case study. Um, um, this was from a pulp and paper mill. The mill engineer, I went to the pulp mill. The mill engineer came to me and showed us a piece of 316L pipe that had been in sodium chlorate service. Normally 316L is sufficient in the ambient temperature sodium chlorate. It will pit if the temperature gets too high, but he declared to us that the pipe that was supplied was poor quality. And he said, my welders are great. Look at the really thick, big weld they put on the material. And we had some questions about this, so we asked him to section the piece. And of course, what you look on the inside, it was clear that they butted the two pieces of pipe up together. So there was no root gap there. They you got no penetration in there, and that's typical for a stainless steel. Carbon steel, you could have done that and probably got full penetration with this thickness of pipe, but not with stainless steel. And so what happened, there was a crevice there where the two pipes butt up, and the uh, sodium chlorate started crevice corrosion. It corroded in various areas, but the shortest distance to the outside was in the pipe, not the weld, because the weld was very thick and it failed. So the problem was weld technique, and the welders didn't properly allow for a root gap there. The next case, it was another place. It was a small diameter butt weld, and obviously the welder took a great deal of care in the external appearance of it. He wire brushed the weld, the heat affected zone very nicely. It was nice and shiny, but what about the inside? And it's because the corrosion environment is on the inside. That's the one that we are most interested in. And so we see, first of all, a lot of heat tint there. And then there was a stop-start defect up at the top of this particular section piece, and you can see that the corrosion had started there. So now, when you're doing the small diameter pipe, it can be difficult to where you finish the weld off and stop it to actually ensure that you have no defects. And this is where skill of the welder is so key to that. Now, they also should have used purging on the inside to avoid the heat tint there, although in this case, the heat tint wasn't the area that was first attacked. It was the stop-start defect. And the third one was it was at a wastewater treatment plant. They take the solid waste and digest them, and you get methane and other gases forming. It's a vertical vessel, and this pipe was off it horizontally, and the particular pipe was used only intermittently, and the sewage, the decomposed sewage, would sit in the pipe for long periods of time, about half filled, and it first leaked at a weld, and of course, first thing they do is blame the fabricator and the welder because it leaked first at the weld, and the rest of the pipe was looked like in good shape. But when you sectioned it, which we always love to do to see what the real problem was, you could see that there was a lot of corrosion in the bottom half, deep pits, big, wide, broad mouth pits, we would call them. And but the top of the pipe was fine. And this is the sewage that sits in there. And the microbes will attack the stainless steel. And as shown in the right-hand picture, they tend to attack welds at the greatest, more than the base material, but they will attack the base material. But the welds are the area that normally first are penetrated, and therefore the leak first occurs at the weld. Had nothing to do with the welder. It was a design problem. And what happened here is that they really should have flushed the pipe out. They should have put a spray nozzle in at the beginning of the pipe and then flushed all the solids out of the pipe, so there was nothing sitting in the pipe, and it would have been completely drained. So that is the issue there. So starting off correctly, well, let's get the scenario here. Let's say you're a fabrication company, you won an order for a pressure vessel in a super duplex stainless steel. 2507 is a common one. It's an alloy that your company just fabricated successfully 6 months previously. Most people, the first time they do a super duplex, they have some initial problems in qualifying procedures and welders. But in this case, it was similar to what they did earlier. The plate thicknesses are similar, no unusual welds. This job should be problem-free. And the end customer, as many in oil and gas and other industries, they'll specify some standard tests, an impact test at minus 40 degrees C, a ferric chloride pitting test, which on super duplex is done at plus 40 degrees C. They want the austenite ferrite ratio in the weld and the heat affected zone to be measured on a trial weld. So you do your trial welds, you use your best welders, of course, but you send it to the lab and it comes back with failing results. And now the job is weeks behind schedule. You've got a lot of money you've done in testing that is not good. Well, what went wrong? Well, of course, there could be many reasons for what went wrong here. But one of the key reasons can be that the material was not ordered correctly and confirmed to be as ordered. It wasn't specified correctly by the fabricator. And because of that, it may not be possible for the welder, no matter how good he is, to achieve the acceptable welds. So the first thing you want to do is make sure that the base metal that was ordered with additional requirements. The two standard ones in industry are ASTM A923 or the ISO 17781 specification. And they give requirements that for the base material to be in the best heat treated condition tested in a way that ensures that. But it isn't sufficient to just specify those tests. You have to actually make sure the mill does that. And you might say, well, of course the mill should do that. Well, they should do it, but we have found sometimes they will actually report typical values. They will not actually test the material itself. And then you should ask for the test to be done per heat treatment lot rather than a heat number. A heat of duplex stainless steel might be somewhere between 50 and 150 tons. The plates may be heat treated in 5 or 10 ton batches, so that you want to ensure that the tests were done per heat treatment lot, because 9 of the 10 heat treatment lots may be done correctly, one was not, and therefore it would fail, and it's impossible then to weld it and achieve the proper requirements in testing. So who's at fault? Well, your purchasing manager has the job of buying, shall I say, the least expensive material that meets the specifications provided to him. So it's really up to the engineering company or the engineering group to come up with the proper specifications, and uh, and that then, if it's separate from the welding department, which at a larger fabricating company is the case, you have to have good communication between what the welding group needs, what the engineering group wants, and then the purchasing manager has to um, uh, make sure that he buys it to the specification. But then it's also important to check that when it is delivered, that everything is in order there. And I say that because we came across a case where the producer of the material, which was a relatively new producer, wasn't from India, I can say, but it was a new producer, and they said, well, we didn't do the test, but if it doesn't meet, if you find it doesn't meet the test, just send it back. Well, that is a bad situation. You've waited a few months for the material, and then it's up to you to test it to ensure it. No, that's wrong. And of course, the standard duplex or super duplex alloys have poor properties if the heat treatment was done improperly, or the chemical composition, especially the nitrogen content, was in the bottom end of the range. Now, the major producers of these alloys, and I'll say, because I was involved with one of them, we've made the mistakes originally, so we know how to produce them now, and how to produce them properly, how to test them properly. But some of the newer producers do not, and so you don't want to be the one that they learn on and make the mistakes on. So it's very important to specify properly and then ensure that the material is brought in, and that all the testing has been done. Well, what about the other stainless alloys? So 6 Moly alloys, the 254 SMO, AL6XN, 1925 HMO, they're also sensitive to inadequate heat treatment. Maybe not quite as much as the duplex, but they still, if poorly heat treated, they will give poor corrosion results. But they may actually meet the ASTM, for example, spec, or any other specs. And this is one issue with the 6 Moly alloys, is that the minimum heat treatment temperature given in the ASTM spec is too low in many cases. So if intermetallic phases have developed during the say a hot forming process, hot rolling, hot forging, um, it they actually need a higher temperature, maybe 50 degrees higher than that minimum temperature, to actually dissolve the intermetallic phases and return the material to the best shape. And of course, there is no heat treatment given in any of the specifications that tells you how long the heat treatment should be at temperature. Everybody has their formulas for counting how much time, and it's typically for plate material of thicknesses, it can be um, 10 minutes plus then 1 minute for every 1 millimeter of thickness. That can be one gauge, but it really depends on how much intermetallic phases have formed in the first place. So typically, I would strongly suggest that whenever you order 6 Moly stainless steels, is that you order them and include a ferric chloride pitting test at 40 degrees C per heat treatment lot again, because you can do 9 out of 10 heat treatments correct, and if one goes wrong, that's where the failure is going to occur in whatever you're building. So what about the standard low carb, and I'll say the low carbon stainless steels? I'll emphasize that low carbon 304L, 316L. They are less sensitive to poor heat treatment. So unless it is a very demanding service, and nitric acid is one of them, these grades normally do not need any extra corrosion testing beyond what is given in the standard specification. So it should be noted, for example, ASTM A240 for plate, the manufacturer doesn't actually have to do the tests. It says the material is only capable of meeting a test, a 262 practice E, or the Strauss test, a copper sulfate test. So in general, these are not done, but if you do have a special case where where it's a severe corrosion environment, it may be beneficial to add some extra testing requirements there on it. And finally, starting off correctly, when you get a material in, and it is any kind of critical service, whether it's chemical, petrochemical, pharmaceutical industry, is important to do a positive material identification on the material. And an example of that that I came across recently, it was a water tank that was in to be built in 304L. It was a 1/2 inch thick, 12.5 millimeter thick plates in material. They had the proper mill certs. They did not do a PMI on it, and it's only 304L. What could go wrong with that? Well, after tank erection, it was a large tank. They did it on site. They filled it full of water and then inspected it. And they had many long cracks parallel to the weld, 2 to 3 millimeters away from the fusion line normally. What happened? Was it the welder? What went wrong? Well, of course, when they did the PMI, they found out that it wasn't 304L. It was one of these low chromium 200 series alloys, mostly used in lower quality kitchen goods. They're less expensive material, and so much less expensive than 304L material. High manganese there. They are known for delayed cold cracking, so you can weld them up or form them and they look good, but then after a while the cracks develop. And then in the case of this particular tank, in the cold worked area, which was the heat affected zone, and it wasn't the heat that caused it, it's when a weld cools and shrinks, it stresses the heat affected zone there to very high levels, maybe even 100% of the yield strength. And the cracks were not observed immediately after welding. They were only after the hydro test. There were tiny, tiny cracks that weren't visible, and then they opened up with time. Now, even reputable stainless steel suppliers can occasionally make mistakes. They can, 304L looks exactly the same as 316L. Most of them will do a PMI on the outgoing material, but they're not necessarily checking every piece. But as a warning, and I just say this without going into detail, there are companies that are out to actually cheat, that are out to defraud you. They will actually know they are selling you a inadequate material, a wrong material. And so it really does happen. Okay, oops, sorry. I'm going to, I was going to have a look at some of the Q&A because I don't know if some of them related um, or whether I'll cover some of them later. Yes, okay. As I go through this, yeah. Yes, okay. Somebody was asking about in my case studies 1 and 2 with the defects there, whether radiography was done. These, there's a lot of cases where it is not done. And one of them was in a pulp and paper mill. They don't have um, radiography. There was no real code, like it wasn't a pressure vessel code there. And so these would have been detected by radiography for sure, but in plants where they aren't pressure vessel, where it's not required, it's not done. Radiography, of course, can be expensive, and if you actually do use X-rays, you have to close off the area so that nobody is harmed by the X-rays. But yes, they can be detected by radiography, but not everything is radiographed. There are some portable units that don't use radiography, but they're not common, and most people just, the idea that when something leaks, then they will fix it. That's a lot of the attitude. Um, and I know I've been to pulp mills in India, for example, and that is their attitude, as well as the ones in Canada. Um, so somebody was asking, I think in case 3 about the operating pressure. There was it was just a pipe that would flush out. They would open up a valve and the sewage would come out there. I'm not quite sure what the reason for it was, but there really was no um, pressure, but they would have to drain it. And so you put the pipe at a slope so it does drain, but the important thing is to flush it out with water to make sure it is clean. Um, oh, let's see now. Okay, I think I'll go on and, oh, just now, there was one here. What precautions for duplex 2205 welding to avoid defects? Okay, we were discussing about this prior to the start here. We can do a whole session, and I have several sessions on welding of the duplex alloys. Um, they it's a whole different scenario than it is with, let's say, the austenitics. And there's some similarities, but there's a lot of differences. And I really think that we should do one on duplex 1 or 2 even on duplex stainless steels.
We'll take your date, Gary. Whenever you're ready, we will do the duplex ones.
Yeah. Well, we have done them, so we can do them anytime. So yeah. Okay.
Yeah, I think we can plan a couple of sessions because it is a very vast topic.
Yeah, good. Okay, so I'm just sorry, I'm just gotta take that out. I think what I'll do is I'll start off on the dissimilar weld here, because it's an interesting session. And I'm sorry, I went ahead too much far here. Here we go. So it's some of the biggest questions that arise are on dissimilar metal welds, and there are often many good choices and there are many bad choices to what you use as a filler metal. So first of all, what's a dissimilar metal weld? Well, you have two different alloys. They could be two different stainless steels. They could be two different metals. They could be a stainless steel and a nickel alloy. And you will talk about this, but you want to weld them with a filler metal. And the weld metal then is a mixture of the filler metal, metal A, and metal B. So it'll be a composition that is not like any of the base materials or strictly of the filler metal either. And you can have any sort of different joint, but it illustrates here. And we often say that 15% dilution from metal A and 15 from metal B. That's just a guess. Sometimes it's more, sometimes it's less. So what do we have to worry about? And we're thinking here of the weld metal, the fusion line, and the heat affected zone. Well, compatibility of the two metals. You can't just weld, let's say, aluminum and stainless steel together easily. There are very specialized techniques where you can do that, but they don't involve fusion welding of the normal types. You have code requirements, whether you need post-weld heat treatment, if you have a chrome moly stainless steel on one side, you also have to think what happens when you do a post-weld heat treatment on it, which is maybe done at 550, 600, 650 degrees C, depending on the alloy. What will happen to the weld metal at those temperatures? You have to worry about susceptibility to various types of cracking, hot cracking in the welds. You have to think about physical properties. The thermal expansion rates, are they similar or different? The melting temperatures can be an issue if you have something that has a low melting temperature and a high melting temperature. And of course, mechanical properties. Are you going to change the mechanical properties of the heat affected zone? Um, uh, in the welding, if it's a quench and tempered steel, you are obviously going to do that. Stainless steel, austenitic stainless steels, you don't. Any changes of properties while it is in service, and we'll talk a little bit about that. The strength, it's not bad if they're roughly equal strength materials, but if one material is stronger than the other, there can be issues with that, because the high strength material, when it cools from the welding operation, it's going to stretch the weaker material. We can talk about creep strength, what is needed for the application in terms of corrosion resistance and strength, creep strength. Ductility issues, toughness, that's cryogenic temperatures, and then corrosion properties. And we can even think about galvanic corrosion. Is that a possible issue? So a few general rules. First, should use filler metal whenever possible, whenever you do a dissimilar metal weld. Obviously, if you're welding material that's only 0.5 millimeter thick, that's not possible, but in most cases, you do want to use a filler metal. Most of the filler metal charts show one choice of filler metal, and that's fine, but usually there's 2, 3, or more. And so you can't just say, if somebody says, I'm going to use this alloy to do that weld, and because you have a chart that says, okay, that's not that alloy, doesn't mean that it's wrong. So, but there are definitely wrong or unsuitable filler metals. And as I mentioned, the amount of dilution of base materials into the weld metal is dependent on the welding process, the weld joint type, metals being welded, whether it's you're doing a low heat input weld or a high heat input weld. So, okay, so let's take an example here. We're going to weld, we built a 316L vessel. maximum operating temperature might be 60 or 80 degrees C. And we're going to weld some mild steel flat bar. We've rolled into rings around it. The vessel is 1.5 meters diameter. What are we going to think about here in the vessel? As I say, it's 316L. Well, compatibility. Well, mild steel to 316, those are two compatible materials, but not galvanized. You don't want to introduce any zinc into a weld that will go to stainless steel, because the zinc will go to the grain boundaries of the stainless steel and cause um, a form of brittle failure. Thermal expansion difference. Well, there is a reasonably large thermal expansion difference between mild steel and 316L. But when we talk about only 60, 80 degrees C, it's not a huge difference. If we were talking 300 degrees C, then there might be a potential problem. Strength, well, they're close in strength. Corrosion, well, there really is no requirement on the weld metal itself, because you've got carbon steel there. So it's hard to have anything that's less corrosion resistant than carbon steel. And if you say it's okay, if you're going to paint the mild steel afterwards, you would of course paint the weld anyhow, or chances are you could anyhow do that. So, and now the only thing I might mention is on the inside of the vessel, when you weld on the ring on the outside, you will get heat tint on the inside, and that is a very bad heat tint, so typically you do want to remove it. But the standard filler metal choice for such dissimilar metal welds is 309L. Now, so what I want to do is go through how we look, what is acceptable, what is not acceptable. Well, first of all, we love to use the ferrite prediction diagram, and this one is one that this is from Avesta Welding, which is now I guess part of the Bowler Group. You calculate a nickel equivalent based on the nickel, manganese, carbon, and nitrogen content. Nitrogen is a little hard to come by sometimes, so you sometimes have to just estimate what it is. The chromium and the nickel equivalent is the vertical axis here. The chromium equivalent is based on the chromium, the molybdenum, and a little bit with the silicon and niobium content. So one way to do it, and sometimes I do it this way myself, is you look at the actual chemistry of the two base metals, and let's say take a case of 15% dilution, you get the exact chemistry of the filler metal, and the weld metal will be 15% of base metal A, 15% of base metal B, and 70% of the filler metal. You actually calculate then the composition of the weld metal and then plot it on this diagram, and you see where it lies. But there's a simpler way of doing it that works in many cases, which I would like to illustrate here, and that's by drawing lines. Now, if I start off that just for this area, A is for austenite, so this area is fully austenitic. This area is austenitic with various amounts of ferrite, so we have 2, 5, 12, or 15, and 40. And most stainless steel filler metals are designed to fall into this area. M is for martensite. Martensite is hard and brittle, can lead to cracking. You've got an area here that is both martensite and austenite. And that's not as bad as the pure martensite. You got to avoid this one at any cost. And then you have areas where you have martensite, austenite, and ferrite, which again is not a good area to be. And then the purely ferritic would be down here. But when we talk about most welding, we're into the austenitic areas. So, okay, so let's take this, look a little closer at this. So if we have carbon steel, here's number 1. Now, carbon steel has not nickel in it, but it does have carbon in it. It does have manganese in it. So generally, you do have some nickel equivalent there. You have very low chromium equivalent. There's usually no chrome or molybdenum there in the standard mild steels. You do have some silicon, so you have a little thing there. So this blue area here represents where the base metal lies on this diagram. 316L, it's a fully austenitic alloy. Nah, if you plot it here, it'll show a little bit of ferrite typically there. So it would lie there. Now, if you were just to weld the two metals together without filler metal, you take your TIG torch and just melt the material so you have a similar metal joint there. The weld metal will lie in this red area, the number 3, and being 50% of the carbon steel, 50% of the stainless steel. Now, the mild steel actually melts preferentially to the stainless steel, but for this purposes, it's roughly correct. So we're into the pure martensitic zone. It's going to be brittle. It's going to be very crack sensitive. You don't want to do it. So that's why you would never weld this combination without filler metal. So why 309L? Well, let's keep the same diagram here. And what we will say is that the, well, first of all, this purple area, I'm not sure how clear that is, number 6, that represents the 309 filler metal, might have 9–12% ferrite in it if you were just to have an all weld metal specimen. So it falls into this area. Your mixture of carbon steel and stainless steel is in this area, and we're going to say that we have 30% of this material and 70% of this material. So you draw a line between the two and you go up this way 70% or down this way 30%, doesn't matter, usually going down this way. And you can see that the composition then falls into an area where it's austenitic with some ferrite there. So it is not crack sensitive. It's what you're looking for. So typically that is why 309L is used here. So what other filler metals could be used? Well, we could use 309 LMO, and I'll talk about each one of these individually. 312 is the one that people sometimes think of for dissimilar metal welds. 310 is often mentioned. Some nickel-based alloys are also mentioned. But we shouldn't use 308L or 316L. Well, let's go and have a look at how they fall here. So we're going to keep this diagram. The 3 is where the mixture of carbon steel and stainless steel would lie. The 309 MOL is this yellow area, and I'm not sure how clear that shows through to you, but it has a higher ferrite content than the straight 309. A little more chromium equivalent, so a little bit to the right of the 309 there. And you again draw a line between this 5 and the 3, and you go up 70% here or 30% from here. You get to this purple area, and again, we're in a perfect range for some ferrite, good crack sensitivity, resistance, so it's not crack sensitive. Again, perfect. Well, what if we use the 312? Well, it has a much higher ferrite content, typically 25–30% filler ferrite content. So it's here. Here I didn't draw the line, but if you draw the line between the 3 and this 8 and do the 70% up this way or 30% down this way, you will see that we're still in an area of austenitic with some ferrite content more than with the 309L or 309 LMO grades, but still for many applications acceptable. And we'll come back into why that is. Well, what about 310? 310 is a fully austenitic filler metal, so that the base metal falls into this area here. It's 100% austenitic. And we go back to that red 3 here and draw the line between the two and go 70% up here or 30% down this way. And you'll see that it falls in the 100% austenitic area. Well, the material is going to be soft, but there can be hot cracking issues, especially if the carbon steel has a lot of impurities in it. And so you really have to be careful. You can use the 310, it often gets recommended, but you have to run it at much lower heat inputs. The cleanliness is far more important. In this case, if the carbon steel is too contaminated with impurities, and that may just be the way it is, there's nothing you can do about it, it may not weld well. So it is possible to be done, but it isn't easy. And if we take the nickel-based filler metals, they're here, and many of them are even off the chart here. Again, you draw the line to here. So typically the weld metal will fall in this range, again, fully austenitic, and the same issues. Well, why would we even talk about welding with these filler metals if we're worried about hot cracking from impurities? Well, when we have high temperature service, the parts going into high temperature service, the thermal expansion coefficients of carbon steel or chrome moly carbon steels are very different than 304L, 316L. And here this particular nickel-based filler metal is commonly used. In fact, the specifications often will say above maybe 350, 400 degrees C, you should use a nickel alloy filler metal to weld, for example, chrome moly steels to a stainless steel. This is preferred in those applications for reasons of similarity of thermal expansion coefficients, especially if the material is going up and down in temperature regularly. Okay, so why not weld 308L or 316L to weld that 316L to mild steel? Well, again, you draw it on the chart, and we can see green here was 316L filler metal, 308L filler metal is here. You draw your line. You're going to end up in the austenitic with martensite present here. So you're near the austenite line. So you have an austenitic weld that has some martensite there. Does it mean that you should never weld it with 308L or 316L? If I was welding a shelf that's going to sit in for a bookcase, and I was using stainless steel for some reason, it's going to work. A little bit of martensite is not going to be a problem. But for most industrial applications, most real severe applications where you're using the stainless steel, you don't want to have the martensite there. If there's any bending involved or movement of the material, the fatigue strength of that weld will be very poor. So in summary, 309 now, we said it's the most common one for welding 316, and I'm only talking here about 304L or 316L to carbon steel. 309L is the typical one that's used. It's the least expensive of any of the ones I've mentioned, and it works in most cases, maybe not the one where you have a higher temperature involved. 309 LMO works similarly very well. It's a little bit more expensive. It flows nicely as a weld metal. The welders love it. Many cases they say, I want to use that filler metal, and yeah, it works in similarly in most cases. There is an issue with bare wire that the chemistry may not meet the AWS requirement. And this is one of those little secrets of the welding industry. They might say 309 LMO to AWS 5.9, A5.9, which is the spec, but the chemistry may not actually meet it. You have to be careful about that when you're doing pressure vessels. The 312, there are some people that sell it and brand it as some spectacular welding electrode because it is highly tolerant of impurities in mild steel, higher strength, but because of the ferrite content, it does have lower ductility, and also you want to avoid it at high temperatures for high temperature service. And again, sometimes the filler metal is outside the AWS composition limits. 310, it solidifies fully austenitic. It's less expensive than the nickel alloys, but you do have to worry about the hot cracking issue. And then the nickel chrome iron 3, nickel chrome 3 materials, they are used in high temperature service, cyclic service. And they are they are expensive filler metals, of course, more expensive than the stainless steels, but you want to use them where you really need to use them. So another type of dissimilar weld metal is when you're welding clad. And again, I could spend half an hour on this topic, but because there are different ways of welding, and we're talking about here stainless steel clad onto carbon steel. So the stainless steel is typically 2 or 3 millimeter thick. The carbon steel is thicker. It could be anywhere from 10 millimeter to 50 millimeter thick. And you could theoretically weld it with a 309L, let's say, if it was a 304L clad material, you could weld it with 309L all the way. But if you have a 50 millimeter thick material, that's a lot of expensive filler metal going in there. So you really want to weld it as much as possible with carbon steel. But then when you weld on the other side, you want to use that dissimilar metal, the proper dissimilar metal filler metal. And if it's a 304L clad, you can use 309 for everything. If it's 316L, you can use the 309 LMO for everything. And then it gets complicated if it's another alloy. And I won't go into that. That could be the topic of another webinar. So, and I know you won't be able to see this very well, if at all, but just for example, the AWS D1.6, which is the welding of stainless steel, structural stainless steel specification there, it has a huge number of charts, overwhelming number of charts. Sometimes it's hard to find the right combination there. But you'll also see that it only gives one choice of filler metal. So it's very useful, gives you some idea of what to use. You can go with their suggestion, that's fine. But there can be other suggestions depending on the, or suitable filler metals depending on the application. This is another one from one of the consumable suppliers, and again, sometimes they'll give one or two possible choices there, but in many cases, there are 3 or 4 choices. So generally, you can't go wrong with these. Doesn't necessarily mean it's the best choice in all applications, but they are suggestions and something at least to take into consideration there. So many of the good welding consumable suppliers do have those charts. And I might say when we get into nickel alloys, and I know we're not talking about them here, The nickel alloys, the nickel alloy producers will also have their recommendations. So let's very quickly look at some of the, when we're repairing equipment that has been in service. That is always a bit tricky, and so let's look at some of the considerations there. Well, I always like to emphasize that the first thing is if you're trying to do a weld repair, health and safety risks are important. If you're doing weld repair on a tank or a pipe that has contained flammable or explosive or poisonous material, you really want to check off first before you send a welder anywhere near that area. Also get the health and safety people involved, let them check off that it is fine. You want to look about the nature of the damage, whether it's mechanical damage, has it been damaged because a forklift truck backed up into a piping rack, or was it corrosion? And what is the condition of the equipment outside the damaged area? So you might have an area that you're supposed to fix because that's where the leak first occurred, but you want to check, well, what about half a meter away? If it's corrosion, maybe it's just waiting to be leaking just half a meter away or 10 millimeters away. So you really want to check to see how widespread the damage is, not just what is visible, but what is actually the case. Of course, you sometimes have to put equipment back in quickly in service. The plant doesn't want to shut down, so they might want just a temporary fix, and then when things can be done properly, you can do a permanent fix. So those are the considerations, and sometimes the production people want a temporary fix where one really is not possible. It's only going to last a short period of time, and you'll be facing the same problem the next day. One of the issues when dealing with equipment in service is what is the exact material, an alloy, and its properties now, including its weldability. And I say that because maybe it was supposed to be 316L, but maybe it failed earlier and somebody put in some 6 Moly material for a certain part. You really want to know what that material is. And sometimes it's important to talk to the plant people to find out what the history of the material. Has this leaked recently? Has it leaked 5 years ago and it was replaced with something else? And of course, if it was replaced with 6 Moly or a duplex alloy and it was supposed to be an austenitic, the repair procedure will be completely different. And the properties, what the properties are now. So if it's been in high temperature service, the properties of the material may change. So a lot of alloys meant for high temperature, whether it's 309 or 310, they may actually start to become brittle with time, depending on what the temperature is there. So they're very soft and ductile when they're put in, but they can become brittle. And weldability will be very, very different. So the accessibility and ability to clean, protect, and prepare surfaces. I mean, if you have a stainless steel that's covered in corrosion product with product from the process, and the welder can only get in there with a wire brush to clean it, he's not going to do a good job. And some alloys are very sensitive to the cleaning procedures. 304L, 316, important to clean, but if they're not 100% perfect, well, you can do a pretty good job with them. 6 Moly and Duplex, you really want them super clean. And then, of course, suitability, if it's a pressure vessel, especially of a or pressure pipe of the PQR, WPS, and the trained welder. And sometimes if the failure occurs on a night shift, and you have to do a temporary fix. Well, of course, you don't have all the good welders on staff there. So you really want to make sure you have somebody who knows what he's doing. So, and I just always refer to ASME has a book called PCC 2. It really talks about repair and equipment, repair of equipment and piping within the scope of ASME codes. After it's been in service, it covers non-metallic, it covers mechanical repairs as well as welded repairs, and various other things. So it is really the standard to go by for repairing. Now, it's not perfect either, and doesn't cover a lot of the special cases. So one of the things to think about, though, is can it be fixed temporarily by a mechanical clamp, for example? If it's carrying water or something not corrosive, you can put a temporary clamp on it, and that'll fix it. It may occasionally still leak a little bit, but if it's a non-toxic, harmless fluid, otherwise it's not a big deal. Put a clamp on it, wait till you can shut down the line to fix it properly. Patches, that's what often people think of, whether it's a pipe or a tank. Generally, we tell people to avoid doing them because, again, you put on a patch and somebody thinks, oh, well, I can just run it for the next 10 years with the patch on. And patches really are only a temporary measure. You have crevices underneath the patch. If you do use a patch, ideally you put it on the corrosive service side, but that is rarely possible. Of course, if it's a pipe, that's not possible normally, but always use round the corners of the patch. Don't put sharp corners there because those are stress risers where you can easily end up with fatigue there. So patches possible, but really should be considered only a temporary measure. Shop versus field conditions. Well, of course, if you can do it in the shop, you're going to be able to clean it properly. The welder can maybe put it on a turntable so he can do it easier. And if you make it easier for the welder, you'll get a better quality weld for sure. If you have gas shielding processes like gas tungsten arc, you can do that properly. If you're in a plant and there can be, wind or breezes blowing that will disturb the gas shielding. And of course, in a shop, you can do proper inspection and testing of it. So it isn't just the welder inspecting his own weld. You can have a proper inspector look at it. When we go back to identifying the material, I won't go into a lot of detail here, but basically, every chemical plant, every petrochemical plant should really own an alloy analyzer. They are not cheap. Typically, they're 25 to 30,000 US dollars. You don't want to let just anybody use it. It has to be a properly trained person, but they are really the best way to make sure you know what you're dealing with when you're going to weld something. And especially with cast components, a lot of cast components don't actually have a standardized grade name on them. They'll have usually the manufacturer's name for a particular cast material on it. So you can spend a lot of time trying to find out what the actual composition is, therefore what the proper filler metal is. But the alloy analyzer, if you have one, use it. Get somebody in to do that. So, weld repair of stainless steel. So, I've divided them into families here, and of course, one of the important parameters is whether they are hardenable by heat treatment. Of course, in by heat treatment, I mean in welding, the heat treatment from welding specifically here. In other words, short time heat treatments, austenitic, duplex, ferritic, no. Martensitic and the pH grades, which are hardened by a quench and temper. Well, sorry, martensitic are done by a quench and temper, pH by another heat treatment, but you will affect the properties of the base metal when you do a repair weld, whether they're ferromagnetic. And of course, some people are confused. Most plates are wrought material are not ferromagnetic at all. They might have a tiny bit of response to a magnet, but not enough for the magnet to stick on them. But welds and castings, because they have a higher ferrite content than the wrought material, they will be much more ferromagnetic, and the magnet may even stick to them that strong. But it's a much less than a mild steel or a duplex stainless steel. So it's easy to tell a little bit about the family from that property. Duplex grades are quite ferromagnetic. Ferritic grades are as ferromagnetic as carbon steel. Same with martensitic grades. pH grades, it depends on the particular grade. But let's look at the relative weldability of them. The austenitic family in general is easy. Yes, the 6 Moly alloys might require a lot more cleanliness, lower heat inputs, things like that, but they are relatively easy. The duplex alloys, it's more difficult because they do want cleanliness. You do have to be careful about both minimum and maximum heat inputs on them. It's easy to get it badly wrong, and by badly wrong, the weld may look great, but it may corrode very quickly in service. And I've been working with duplex stainless steels since the mid 1970s there, and my expression for them is when they're good, they're very good. When they're bad, they're awful. It is that way. The ferritic stainless steels are very difficult to weld. You don't see a lot of them, mostly heat exchanger tubes, and you wouldn't want to weld repair them anyhow. And the martensitic and pH, the hardenable ones, they are difficult, but it is possible to do temporary repairs on them. So why are austenitic ones easier to use? Well, first of all, there's really no change in microstructure when you expose them to temperatures ranging from, well, absolute 0 to about 400 degrees C. And I would even go a little bit higher on the temperature there. Yes, above 400 degrees C, you can get some carbides forming, but you don't normally get a lot, and they are well dispersed. They're less harmful types of chlorides. But you can, or sorry, carbides. I didn't say chlorides. Carbides between 400 and 900, you do have carbides forming. Generally, they don't have a large effect on weldability on wrought material because the carbon content is generally 0.8 carbon max. But when you get into cast materials, the carbon can be very high. And for example, the HK40 has 0.4% carbon. It's meant to form carbides because the carbides give it a high temperature strength, but it definitely affects the weldability of it. But generally, if you have 304, 316, even if it's not specified as low carbon, the carbides may affect the corrosion resistance, but they may not affect the weldability of it. Above about 525 C to 1000 degrees C, you can get some embrittling intermetallic phases. So 309, 310 can embrittle, a lot of alloys can. That are meant especially for high temperature, but the 18.8, the 304, the 321, 347, they don't embrittle very easily. It can take 10 or 20 years for it to embrittle. So they will eventually, but you don't run into that so often. The welds in cast material will typically embrittle faster than the wrought material because the ferrite phase there will form the sigma phase, which is the embrittling intermetallic phase. The higher chromium, higher molybdenum stainless steels form the intermetallics quicker. So you do have to be concerned a bit about this when you're dealing with some high temperature alloys, high silicon alloys, also, which are very rare in industry. So nickel and nitrogen slow down the formation rate of intermetallic phases. I guess a comment, but even those that have nickel and nitrogen in them will eventually embrittle. So let's look at reformer tube alloys. They're working at a high temperature in a petrochemical plant. If they've slightly carburized on the surface, you're forming carbon enters the stainless surface from the outside. They are especially tricky to repair and indeed may not be possible to repair. So you have a carburized layer on the surface, it's heavily oxidized. You really need to remove that carburized and oxidized layer down to solid base metal, the original base metal. You may have to do a solution anneal at 1065 for 2 hours is a typical treatment. That's obviously not very easy to do when it's in sight, but these reformer furnaces are huge. If you really try to get it back up online, you really want to do it in line. It's expensive, but it is often the only way to do it. And typically we do a test weldability, a TIG bead on plate weld. If you do get cracking, you grind back a bit more, do it again until you get one that doesn't crack. And with reformer tube alloys, there are new filler metals being developed for repair welding. A group that I belong to called MTI, Materials Technology Institute, has several programs on weld repairing of reformer alloys. Okay. So the weld processes. So normally, unless we can do it in a dry, clean metal with no drafts, we want to use a process that has a flux on it. And that would be a stick electrode is the most common and the best one by far. Flux core welding may be possible. If it isn't dry and clean, avoid things like TIG and MIG welding. So cleanliness is important, and that really means if it's been in a caustic service, you want to not just wash the caustic off, you want to put an acid on there to ensure all the caustic is gone. Because the caustic will go into little cracks and pores in the material and cause problems in welding. So if you can't ensure that the material is dry and free from contaminants, the -15 coated electrodes, shielded metal arc electrodes, are really the best. They are the least crack sensitive, the most least sensitive to moisture. And small weld beads, stringer beads, no weaving, low heat input, let them cool between passes if you are doing it in sight there. It's better to put in many small welds than one large weld, which is not how the welder normally thinks, but is important when you have contamination or possibility of contamination. So filler metal selection, if you have a corrosion issue, you can think about using an over-alloyed filler metal. So instead of using on if you're weld repairing 304L, instead of using 308L, which would be the normal filler metal for that, you could think of using 309L. Why? Well, 309 has a higher corrosion resistance, better hot cracking resistance in welding because it has a higher ferrite content. It is easier for the welder to use and get a good weld with, and it may offer better erosion corrosion resistance. However, the downside is the higher ferrite contents of the 309 can embrittle with long time exposure to high temperatures. So if it's a high temperature application, often the ferrite content in the filler metal, whether it's for 308L, for example, it will be limited to maybe max 8 or 10% ferrite so that you don't have a large amount of ferrite in the weld. And 309L may not be as good at cryogenic temperatures. You can actually then use 316L on 304L normally, where you know that the 316L has a higher corrosion resistance. And generally that is the case, but there's always exceptions. So for example, nitric acid 316L is not as good as 304L. In the pulp mills, which I dealt with a lot in my earlier years, they like to use this 309 LMO electrode instead of 316L for welding 316L, and especially for weld repairs. Higher corrosion resistance, better hot cracking resistance, easier for the welder to use, better erosion corrosion resistance. But again, like the 309L, can embrittle at high temperatures, may not be as good at cryogenic temperatures, and it may not be as readily available. You can use 317L on top of 316L. That's generally perfectly acceptable. There are very, very, very few cases where it would not perform better than 316L. Now you might say, well, what about using an overalloyed filler metal? What about galvanic effects? Well, generally within the austenitic stainless steel family, you don't have to worry about that. And if there was any, you have a highly alloyed, more noble weld metal, which is a very small surface area, which is the cathode, and the base metal will be the anode, the least corrosion resistant material. So that's a very favorable area combination. So generally, it is completely acceptable to weld stainless steels with a higher alloyed filler metal. I'm going to mention Duplex here and say it is very complicated with them, and it's especially when you're trying to do a weld repair. The procedures for welding them are different depending on the grade. We have lean duplexes, we have low alloyed, we have standard, we have super duplex alloys. They are all welded slightly different, and even some alloys within that category can be welded different. The cleanliness and dryness is even more important. Any moisture on the surface, when you put a torch to it, like a TIG torch to it, you will generate hydrogen, the ferrite will embrittle, and you can end up with a lot of cracking. As I mentioned, the heat input control, there's a minimum heat input necessary for duplex stainless steels, which is not needed for the austenitic ones. So that means you can't put too many small welds on, or well, you can't put small welds on it in many cases. Again, the shielded metal arc electrodes are better because it reduces the risk of high ferrite in the weld. Use of overalloyed duplex filler metal wherever possible. In other words, weld 2205 with 2507 when you're doing a weld repair, and the pickling cleaning is important afterwards. And just a comment, you have to think about what kind of corrosion is involved, whether it's general thinning, localized corrosion, and I'll go through this fairly quickly, but one of the issues if you're trying to weld repair surfaces that have pitted, there's often hundreds of pits on there, difficult to repair. You got to grind out to the bottom of the pit. Typically, you would use a TIG welding to repair them, but you want to really ensure that the conditions that cause pitting don't occur again. You really want to do a replacement of material. Crevice corrosion, if you have a flange that has crevice corroded, you can grind the material down to sound metal, clean with a solvent, and then weld with an overalloyed filler metal, put on the lathe and machine in the new surface. One of the most challenging is where you have cracking, and especially stress corrosion cracking. It can be very challenging to repair these. And again, sometimes the welder will see one crack and he'll start weld repairing it, and more cracks develop, and then he chases them and he spends then a full shift trying to repair them, and he still has cracks. So that's always a challenge. And I'll just have two thoughts about post-weld treatment on, I know Graham has talked about this, but if the service involves halides, and by that we mean chlorides, iodides, and bromides, where pitting could be an issue, really it is important to remove any slag, and pickling will improve the welds. Pickling of the weld will also help for visual inspection of start-stop defects on the exterior surface, maybe not the interior, and will uncover other areas that are not perfect. Food, beverage, pharmaceutical, high purity products, of course you want them to be clean as possible, so you typically grind the weld flat, and then pickling is a good idea to do afterwards. And if the service involves chemicals which result in light general corrosion, often a little bit of heat tint is not removed. And finally, pickling is a good way to remove iron contamination. It removes the heat tint. Even if it isn't an issue for the service life, it gives the appearance of a good quality weld. Passivation, pure passivation, which is done with citric acid, maybe nitric acid, is a lot of shops like to use it, but it only removes light iron contamination, doesn't remove heat tint well, and especially the underlying chromium depleted layer, but it is useful, necessary for food, pharmaceutical, beverage. Okay. Thank you. That's the end of the presentation. I think I may have run a little bit over long, but anyhow.
I think that's fair enough, but I guess the way you are going, people didn't want to, get away from the topic. It was really interesting, and you covered a great deal about the topics, and especially with the in-service part, I guess a lot of people got the answers. There are a lot of questions both on the chat and on the Q&A. Would you like to take some, Gary?
Sure. Have you chosen some?
There are some from the top 2 or 3, and then we can deciding on that we can just take a look. There's one which has their steel casting manufacturers. They're finding cracks in the weld areas after post-weld heat treatment. Casting grade is CF8C, Navadium stabilized stainless steel casting. Welding electrode E347-16. After welding and penetrant testing, we do not find any cracks, but after PWHT, cracks are appearing at the weld areas.
Yes, castings is an interesting area, because a wrought alloy manufacturer, somebody's making plate or bar, they have very good refining processes to take out a lot of impurities, and especially sulfur content. Most foundries, casting places, don't have that option. They melt, they buy scrap material, use some new whatever, nickel, ferrochromium, this sort of thing. But often the sulfur content, the phosphorus content are quite high comparative to the wrought material. And the others, if it's a very thick casting, you also have a very larger grain size. Most wrought material, you're rolling it or forging it, and it reduces the grain size, whereas with castings, you don't do any cold work on it or working of the material. So therefore, they are far more sensitive to cracking. So the first thing I would do is look at what the impurity levels are in the casting, specifically phosphorus and sulfur. I might look at some of the other ones. I would get the full analysis there to see if that was an issue. I would look at the grain size, and sometimes you can do to avoid large grains, you know, there's different ways of when you're casting it to get the metal to cool quickly once you cast it, so that the grains don't have time to grow to a large size. When they're large, all the impurities are pushed to the grain boundaries. You have fewer grain boundaries, larger amount of impurities there. So it's a really tough question to answer, but do some investigative work along those lines.
So the next question, Dr. Krishnan, would you like to choose a question?
Yeah, give me a minute.
Okay, so the next question there.
I will take this one. The repair welding procedure of aged or used material be the same as original? Will there be change in filler metal? What other precautions need to take? So this is regarding a repair weld where the material is already aged.
Yeah, and that certainly you don't need to do anything different if you already have the procedure in place, but you do have to ensure things like cleanliness is there, that the material is not contaminated in any way. That's where most of the problems in repair welding occur. And it is also the, you know, if you're in the middle of a chemical plant, and it can be difficult to ensure cleanliness. But yeah, you would use the same procedures as you did for the, you can use them. It may not necessarily be the only way to do it though.
I can see one question on heat tint.
That's where.
Yeah, I can see a question on heat tint. Is there any acceptance standard or norm?
Yeah.
For the heat tint that comes with the welding.
Yeah. No, that is a very much asked question. There is an AWS standard that shows that and the number escapes me right now. Is it 1.9? But there's two